Okay. Well, thank you all for joining us. I'm very happy to introduce our own Dylan Slack. So Dylan is a PhD student in the CS department here at UCI, where he's advised by Professor Samir Singh. He also does some work with Hema Lagaraju, who's at Stanford University, at Harvard University. And so he's been doing a lot of really interesting work at kind of the intersections of robustness and reliability and trustworthiness of machine learning methods, especially as these intersect with natural language processing. And he's going to be telling us about some of this work today. So
awesome.
Go ahead, Dylan.
Yeah, thanks so much for that introduction, Eric. Yeah, so if you guys don't know me, I'm a third-year PhD student now. I'm here at UCI. I mostly work with Samir and people in the UCI NLP group, but I also actively collaborate with another group at Harvard University under Hema Lagaraju. So today I wanted to give an overview of my research over the past couple of years in sort of more of a narrative form, in particular looking at these types of machine learning explanations, which we call post hoc explanations for ML. And in particular, I kind of want to divide this between looking at shortcomings of these methods and also what we're actively doing to improve their reliability. So with that in mind, I really have a couple goals for today. I want to introduce machine learning explanations, in particular, this type of post hoc explanation. I kind of want to tell you like what these are, give you a solid basis for understanding research that goes in this direction, and try and convince you why you should care about these. I also want to look at where these methods fall short. What are the current issues with these methods that people are thinking about? And then like, what are we actively working on now to make them better? So what are researchers doing in this direction to improve these techniques? Really, this work would not be possible without a number of my collaborators. So in particular, Sophie, Hema, Samir, and Emily, and also support from various fellowships and awards at UCI and beyond. So thank you for helping with this work. So in order to provide like a foothold into why we might want machine learning explanations, I wanted to start with a sort of a simple example, building a classifier. So maybe this is something we can all connect with. We've all collected some data, tried to train a model. So let's look at where post hoc explanations fit into this build a classifier narrative. And in particular, I'm going to try and build a model that learns to tell apart birds and dogs. So maybe I want to load this model on my phone, snap a picture of a bird or a dog, and it'll tell me if it's a bird or a dog. So that's what I'm going to try and do here. So whenever it sees like an image that looks like this, it should say bird. And whenever it sees an image that looks like, like that, it should say dog. So in order to build a model like this, maybe what I do is I walk around my house. I snap a bunch of photos of my dog. He's usually sitting on the couch. And then I go outside and take some photos of the bird, get them labeled and proceed from there. I shuffle up my data and let's just say I use like a deep neural network, do some gradient descent and train my model. And then I start to do some validation here. So I start to inspect the predictions of this model to see if it's working pretty well. And I'm seeing some promising results. So I'm seeing images that look like this and it says dog. I see another image like that, looks like bird and it says bird, and so on and so forth. So I'm getting pretty satisfied with this model. It sort of seems like things are working out. Because I've used this deep neural network model, I've really built sort of a black box. I don't know why it's making certain decisions. Should I trust this model? Is it making decisions in a way that I would sort of understand? Do I know like which parts of the dog it's looking at? Do I know, can I sort of like fully trust and understand this model? And in particular, if something goes wrong, do I know how to fix it? Is it an issue with the data? Is it an issue with something in my modeling procedure? I sort of just really inspected inputs and outputs and seeing that like in a lot of cases, it seems to be predicting bird and dog pretty well. And in fact, when I bring this model into the real world, I start to see some issues. So I take my dog on a walk, snap a picture of him, and all of a sudden my model predicts bird. This is a bit concerning and surprising to me because I validated it and it seemed like things were working well in the past. So really, I'm interested in this question now, like, why is my model performing badly in the wild? And maybe this is something we can all connect with. We've all there's a good chance a lot of us have built models and validated them, and they sort of failed when they've gone into application in surprising ways. So there's a lot of ways I could proceed from here, but the way we're going to look at right now is these types of post-hoc explanations. And really what these methods do is they take some data input. So they're going to say for the image, what are the important parts of this image that led to a particular prediction? So if I run post-hoc explanations on some of my data, so I get this image of the dog, and what this explanation is really saying is that, okay, it's kind of saying that like, okay, this part of the couch is really important for the prediction. So the areas you can see in this image are sort of the important parts. And then I proceed to the next image, and okay, it's also a lot of the couch. Okay, yeah, it seems like this model is really using the couch to make the prediction. So it sort of seems like I've really built a couch detector here and not really a dog and bird detector. And sort of if you think back to how I generated the data, I only took photos of my dog when he was inside and sitting on the couch. So there wasn't really enough signal there for my model to figure out like the real difference between birds and dogs. It sort of could just rely on this couch signal. And post-hoc explanations are one tool that can help me figure this out. So they sort of showed me that the model was relying on the couch to make decisions. And even though this example is a little bit contrived, I sort of set up the model to do this, and I designed the data collection procedure to sort of enforce that this occurred. These sorts of issues really do occur in the real world, and post-hoc explanations can help diagnose these issues. So there's this really interesting example from the Washington Post where an interview system that was provided by a company was basically using the background of the image to help make some predictions. So when you just simply like swapped out the background of the image to a bookshelf, like people appeared more open, conscientious, extroverted, sort of all these things. And this is how these sorts of issues might manifest, and we can really use post-hoc explanations to try and help figure this out. So with that in mind, we've seen a bit about how we could use these methods. But from here on out, I wanted to take a little bit deeper dive into what's actually going on with these techniques and try and convince you why you should care about them. So what explanations do is they say, like, what parts of the data are most responsible for predictions. So if I had some data instance X and it was fed into my model F and provided outcome Y, these sorts of explanations would say, like, what are the important parts of my data X that influence this model F to reduce outcome Y? And really in explainability, we try and build explanations that work across many different applications. So ideally, X could be like an image data. It could be some natural language text like this. It could be some structured data that looks like that. In all of these cases, I might be interested in like what parts of the dog are being used for prediction, as we've seen, or it could be like what words are used in the natural language to lead to a prediction, like the combination of words, ordering these things. And then in the structured data, it could be like, is it age more important for a loan prediction? Is it income? These sorts of questions is what we're interested in. And because we're trying to build explanations that work in a lot of different settings, sort of agnostic to the model being used, we're really trying to look across the whole entire decision surface of the model. Or we're trying to like narrow down the decision surface just to individual points. And sort of we take all this, we take like what we're trying to do here and build model agnostic local explanations. So instead of explaining like a complex decision surface on the whole, which might be quite difficult, we're instead trying to explain just individual instances because this could be a bit simpler. So if we had like our dog and bird classifier here, and the bird classifier was this purple area and this white area was corresponded to the dog, we would sort of note that, okay, like this is probably a bit complex. If you're trying to offer an explanation for this whole entire thing, it would be difficult. And if we could do this really well, we might just want to use that model in the first place. So instead, what these types of explanations try and do is they say, just for an individual point, how can I give a more locally accurate explanation just for this point? So again, like this decision surface is complex and hard to explain on the whole. What we're going to do is just zoom into this one point. And we can already see that, like, for this particular example, maybe the decision surface is much more locally linear. So how we're going to proceed from here is just fit a very faithful interpretable model in this one locality. So because this model is, models tend to be a bit less complex if we zoom in, a lot of the time we can fit these locally faithful interpretable models. And this is really what we take to mean to be a local explanation. And I want to emphasize this term model agnostic. So again, one of the goals I've said is we want to build explanations that work across a lot of different settings. And kind of the reason these local explanations can be model agnostic is that we only really need points that are sampled nearby the instance we're trying to explain and the model's response in order to fit these types of local explanations. So in particular, if this like green instance is the one I'm trying to explain, what I can do is just with some notion of locality or way to sample points that are like nearby this instance, I can sample a point, get the model's response. So maybe probability blurred equals 0.4 here. I can just keep doing this. And then just using these samples in the model's response, I can fit this explanation. So like the key thing I want to emphasize here is that we didn't inspect the model's internals. We didn't get gradient access. We didn't do any of these other things. We just took these perturbations and got the response and fit this model. And in particular, what an actual model agnostic local explanation would do, this one is called LIME. It's one of the more popular types of model agnostic local explanations, is it would take some instance. So like this original image here, and it's classified as a dog with 0.8 probability. And you would sample a set of perturbations. So these perturbations just correspond to versions of the original instance with parts of it masked out. So images, a lot of the time, this is you just like gray or black out parts of the image. And then across many perturbations, what LIME does is it takes a classifier, it gets the model response. And again, it does this over many perturbations. And what we can start to see here is that when we mask out certain parts of the image, the model's response changes more. And using this as a signal, we can figure out, the important parts of the model, with the idea that if we remove some more important parts for the model's prediction, we should get more of a change. And then with all this in mind, LIME like upweights perturbations that are closer to the original instance because they're sort of more informative about the local decision boundary than it downweights ones that are farther away. And then it uses this information to fit a weighted regression using the perturbations as the features and the model response as the target variable. And then it outputs something that looks like this. So in effect, what this says is that these green areas here correspond to regions in the image that make it more likely to be a dog. And the red areas correspond to regions in the image that make it less likely to be a dog. So you can take this particular explanation to mean maybe the ears and the eyes make it more likely to be a dog. But for whatever reason, this part of the dog makes it a bit less likely. Now, with these types of explanations, these local model agnostic methods, there's really quite a few trade-offs. And this is going to sort of inform our current research directions and the works I present to you next. So these methods are really quite flexible. You only really need query access to the model to fit these types of explanations, as we've seen. They're quite easy to use. You can just hook them up to your model, get a lot of predictions, and fit an explanation. Many of these methods have quite nice software packages, which makes them useful. Yeah, and overall, they're just quite highly flexible because you can customize lots of different things for different types of data. You can change the perturbations. You can define different notions of locality. And all these things can be customized. And they really do provide a rough understanding of what's going on inside a model. And the big disadvantages with these types of methods is that they're highly sensitive to how these perturbations are sampled. And this is going to be a bit of an ongoing theme for today. What the explanation looks like when you fit it is going to be greatly influenced by the perturbations. And this is a big part we're going to try and improve on. And one way to think about this is if I have some like high dimensional data and I sample a set of perturbations and fit an explanation, I might get a totally different explanation if I just did that again, because I might have a different candidate set of perturbations. So this really leads to a number of issues that have to do with stability. Explanations can be unstable. How we go about defining locality, sampling, all these things require hyperparameters, which can make them a bit difficult to set and sensitive. And it's really like one of the key issues here is that as we change all these things, it's quite hard to figure out if you have like a good explanation. A lot of these techniques will just spit out a set of feature importances, like that image of the dog with the green and red areas, without a lot of context. So for people using these methods, it's quite hard to trust them. And this has sort of been shown across many different application domains, ranging from things like medicine to finance to law, where people get explanations and see some that are a bit faulty and sort of lose trust in these methods. So one of our initial works trying to figure out like how trustworthy post hoc explanations are, we sort of took this idea of untrustworthiness and in some sense like took it to the max. So we asked, like, in the worst case, can you design a model that completely fools post hoc explanations? And by completely fool, what I mean is that if you have a model, can it make one set of predictions, but the explanations for that model say something completely different, and they're unfaithful to what the model is doing on the data. So can you do this? And the result is yes, you can do this, and we're going to see how. So we imagine this scenario where you're interested in using post hoc explanations to do auditing. So I'm an auditor, and what I'm going to do is I'm going to run post hoc explanations on some data and see if the person who designed a model is using like discriminatory behavior or is being bad in some way with how they designed the model. So this bad actor, as we call it, has designed the model in such a way that across some data, it makes discriminatory decisions. And I'm going to run post hoc explanations and try and see if the model is fair. And in particular, the way I'm going to use post hoc explanations is I'm going to look at features, like sensitive features like race and gender, and I'm going to see if they're important for predictions, which would indicate that maybe something bad is going on. So exactly, I'm going to look at the explanations and see if the model looks fair. And in fact, it's possible for malicious entities to design these types of models that do one thing on the data, but the explanations look completely different pretty easily. And kind of the key intuition behind this work is that if we have some original like distribution of data, so you could imagine like all the images of dogs or something like that. And then we go and fit our local post hoc explanations, something like Lime, between these original images and these sample perturbations. They're actually quite a bit different. And in particular, if you look at these perturbations, you'll see like these areas of the image that are all blacked out, right? And really, none of these would ever naturally occur in the data. You would only have dog images that look like this. You would never have images that would have these big black spots in them. So consequently, it's really quite easy to design a model that does one thing on these original dog images, and then a completely different thing on these perturbations. So what the bad actor could do is that for this original set of images, they could have their classifier do the discriminatory or bad behavior, right? But the thing is, on these perturbations, they could have their model do something completely else. And because techniques like Lime only use this set of perturbations to fit the explanations, the perturbation or the explanations would only explain the behavior on these perturbations. So if they set up their model to be fair on these perturbations, all the explanations would look fair. So to see a real world example of this, where this type of attack is successful, one of the applications that we considered in the paper was this attack on the Compas Recidivism dataset. So if you're familiar with this dataset, basically, or if you're not familiar with this dataset, basically what it is it's predicting rearrest. And it has features like sensitive features like race and gender, but it also has features like people's criminal history, their age, and things like this. So let's just say that the bad actor is interested in designing a model that only uses the race feature to make decisions. And this is what you would get if you ran Lime explanations across the test data for just this discriminatory model without the attack. And what this graph here means is that this is the percent of the time that a particular feature appeared as the first, second, or third most important feature in the explanations. So what we can see here is that without the attack, the race feature appears as the first most important feature on all of the test instances. Okay. And then the second and third are sort of just the other features in some kind of random order in the data, because they're not really used. But when I run the attack, what I see is that a completely different feature is listed as the most important. So we introduce this like uncorrelated feature here, and uncorrelated is just uncorrelated with this race feature. And it's listed as the most important feature across all the test instances. And sort of the kicker here is that between these two models, so this non-adversarial model and this adversarial model, the predictions on the test data are exactly the same, right? So these two models really haven't changed. It's only really the explanations that have changed. And you can take this as far as you want. You can introduce more features. You could design custom explanations for like particular instances, for many different combinations of features, and so on and so forth. So we can really take this to mean that the attack is quite successful. So this is just one way to see about how like impactful these types of attacks could be in sort of the worst case. The story doesn't really end here. We extended this line of work towards other types of explanations. I mean, this is a brief aside from our inquiry on post-hoc explanations. There's this other really commonly used type of explanation called a counterfactual explanation. And basically, it's concerned with this problem where if you receive an in some way unsatisfactory response from a model, so if you want like a loan or something like that, and your application is fed into a classifier and you're denied, what counterfactual explanations would tell you is that you need to make like $1,000 more a year. So we're sort of find like a minimal set of changes that you would need to make to get the outcome you want. So if this person made $1,000 more a year, they'll get approved, and that's basically it. And these methods basically work by taking some original instance X. So let's say this is a loan classifier, and there's this granted loan region and denied loan region. CFEs would basically say, we're going to follow along the gradient of an objective, define an instance C that is nearby this original instance, but also receives the correct classification. So this objective G generally optimizes like two things, that this counterfactual is in the desired class, but also minimizes the difficulty of C. So incorporates some notion of distance that measures like the relative difficulty of any feature change. And we sort of envisioned counterfactual explanations being attacked in a very similar way or a somewhat similar way to post-hoc explanations. So you have two groups in the data. perhaps men and women, who are denied loans, the bad actor could set up the model in such a way that counterfactual explanations would appear fair. So across these two groups, if you ran counterfactual explanations, it would look roughly equivalent. So it would say like, you need to make $1,000 more a year for both of these people. And like, and if an auditor comes in and like inspects these, they would say, looks fair. But the bad actor can set up the model in such a way that under a small perturbation, something else happens. And by small perturbation, we just mean a change to the set of features that is virtually indistinguishable. And what the classifier would output here is that under the counterfactual explanation, this person would only need to make like $10 more a year, so that the actual difficulty of achieving the counterfactual would drastically decrease. So this is just another way that a different type of explanation can be attacked. And kind of the key idea is that this counterfactual explanation search can converge to very different local minimums. And you can actually design a model that is like very unstable. So if we had an instance X, we could set up the model in such a way that, optimizing this counterfactual objective would lead us all the way over here. But if we just perturbed instances slightly, we could end up in a region that's like very close to this original instance X. So this attack is based on like designing these types of models that are very unstable. And that's a brief insight into that work. We published this paper at NeurIPS last year and sort of encourage you to check out the full paper if you're interested in this style of attack. I'll take a brief break for questions, if anyone has any, before diving into what we're doing to build more reliable explanations. So yeah, if anyone has any questions or anything like that, happy to take some. Otherwise, we can just keep going.
I have a question. So in page 32, you mentioned that the first, the explanation method kind of mistake from the second uncorrelated feature. So I was wondering, this uncorrelated feature, is it really uncorrelated with the race, or is it, did you check the real correlation between the race? Maybe it is identified as important because it's highly correlated with the race.
Yeah, so I think that's a great question. Really, what we did here is we made sure that this feature was not correlated with race. So we could sort of be sure that these sorts of issues, like you described, didn't occur.
So it's uncorrelated in terms of such as a Pearson correlation or linear correlation is.
Yeah, I think we did something like Pearson correlation for this. I would need to check back exactly how we checked that, but I think it was like Pearson correlation. Yeah.
Okay, thank you very much.
Yeah, thanks. Great. Maybe we'll keep on going here. Cool. So I've sort of talked about a lot of downsides of these types of explanations. So I don't want to get you too down on the usefulness of these types of explanations. Really, what I've shown is that in the worst case, it's possible to fool or manipulate explanations. But I really do think most of the time these methods are quite useful about getting a sense of what's going on in models. And there's really a number of things we can do to actively improve explanations and sort of things we've done. So the next part of this talk sort of concerns this paper we wrote, reliable post-hoc explanations, modeling uncertainty, and explainability. And one of the things that I talked about with explanations is how sensitive these methods are to hyperparameters. And in particular, changing the hyperparameters can lead to drastically different results. And without ways to figure out like a good explanation, it can make reasoning about explanations a bit difficult. So to see how this might manifest, I have two explanations for the same instance on the Compas recidivism prediction dataset. I've just pulled out two features here. And what I see is that between these two instances, so as a reminder, these are the same instance, and I run Lime explanations twice, just varying the hyperparameters. The most important feature completely changes between these two explanations. So this one on the left-hand side, it really looks like a misdemeanor charge is the most important, but the one on the right-hand side, it looks like female is the most important. So what Lime would do is it would spit out these two explanations, and it would be a bit tricky to figure out, like, do I trust the one on the left? Do I trust the one on the right? All I really see are these green and red lines on the graph. So our key idea in this work is instead of incorporating just point estimate notions of feature importance, we're going to instead define them as distributions. So now inspecting these two explanations, I see something a bit more promising. So between this explanation on the left-hand side and the one on the right-hand side, this one on the left-hand side has a lot of uncertainty associated with it. And what this indicates to me is that I probably need to learn a lot more about the local decision surface with this one in order to have a confident explanation. But this one on the right-hand side, I'm much more confident in the feature importances, so I can probably trust this one. So we see by incorporating some notion of uncertainty, we can do things like reason about different explanations much more easily than we were able to before. That was for a tabular example, but we can, because one of our goals is to create explanations that work across many different types of methods, we can also do this for like images. So here is a Lime explanation on this dog image. It kind of looks like this area might negatively contribute. Maybe these green areas positively contribute. We can run our new method, which we refer to as baseline. We can sample from the posterior of our method and see that, wow, actually there's a lot of uncertainty associated with this one part of the explanation. And we're just quite confident that this one green area contributes positively to the prediction. Now, to actually go about fitting this method, we're basically going to take the weighted linear regression setup using Lime and convert it to a Bayesian locally weighted regression. So in particular, we're going to define our feature importance as S5, our perturbations as Z, and we can sample a set of perturbations that looks like this with the original instance here. And we're going to weight the error in our regression based on the proximity of the instance, depending on how you define the weighting function. We're also going to fix some priors on the feature importances and the variance of the error. And then fitting this model, we're going to see something that looks a bit more like this. So we're going to get our locally faithful explanation, but we're also going to get some notions of uncertainty along with this. And in particular, what this method provides is sort of two different notions of uncertainty. So it's going to provide us with feature importance uncertainty as we've seen, which defines uncertainty for each of these different features like female or misdemeanor charge. And we're also going to get a notion of uncertainty that has to do with the error of the model. So in particular, how well does this local explanation fit the decision surface? So you can imagine in situations where it's like very linear, be very low, but much higher in some of these nonlinear cases. One of the key questions we initially wanted to ask with this work is like, okay, we can get these notions of feature importance uncertainty, which we think are useful, but how can we really trust them? So we did a lot of work to assess like the calibration of these feature importance uncertainties. So with our baseline method, and we also had this one called Bayes Shap, which builds off this other type of local model agnostic explanation. Basically, what we did is we assessed calibration across many different data sets and models, basically by fixing or running an explanation for a small number of perturbations, and then running it with many, many more perturbations, and assessing how often this like ground truth converge feature importance falls in the 95% credible interval. And kind of really what you need to know here is that values closer to 95.0 are a bit better. And what we observed is that this baseline technique really had quite calibrated feature importance uncertainties. For this other technique-based SHAP, it was a little bit less so, but still close enough that you could take this to be informative. One of these other things I've talked about is how difficult it is to set key hyperparameters for the explanations. So in particular, the number of perturbations you use to fit the model is often a finicky number to figure out. So we leveraged uncertainty to better inform how many perturbations you need to sample in order to fit explanations just with a user-specified notion of confidence. So with this in hand, we defined an estimate, which we called perturbations to go, which would effectively say like an integer valued number of perturbations you would need to get an explanation with like a specified level of confidence. And in order to use this estimate, basically what you need to do is sample a small number of initial perturbations. And using these perturbations and kind of how locally linear the model seems, our estimate will output like how many additional perturbations you need to run to get this good, highly certain explanation. So kind of the intuition here is that if you sample a few perturbations and you get this very like locally linear distance surface, what the estimate is going to say is that you don't need to sample so much more. In the nonlinear case, maybe something like this, the estimate's going to be like, it looks pretty nonlinear. You're probably going to need to sample like a lot more to get like a confident explanation. In particular, we came up with this nice formula that relates things like the local error of the perturbations you sampled so far, the proximity of the perturbations, and the desired uncertainty to how many perturbations you need. And really what this does is that it provides some like intuitive things. Like if you have larger local error, you need to run with more perturbations. If you want to have like less uncertainty, you need to run more. And if the perturbations you already sampled are like very close, they're going to be more informative about the local decision service. We also leverage uncertainty to sample more efficiently. So we came up with this technique, which we called focus sampling. And basically what it is it's a variant of uncertainty sampling. And kind of the idea is we have like a candidate set of perturbations, we can use the posterior predictive distribution of our model to rank perturbations based on uncertainty, and then like and then effectively prioritize perturbations that we have more uncertainty about. And these are going to be more informative. So if we had something like this, and I had like these three perturbations that were low uncertainty, and I sampled this last one, which happened to be high uncertainty, I would just select this one. Maybe another way to see this is if I happen to like bias my sampling over here for my cat and bird or dog and bird model, what focus sampling would tell me is that I would probably need to sample a bit more over here. And interestingly, we saw quite a few benefits of including this focus sampling scheme in a number of applications for explanations. One big thing we saw is that if you use this technique, you can get explanations to converge much more quickly because we can prioritize perturbations that are more informative earlier on, and we get quicker convergence. And we also saw a lot more, we also saw improved stability under focus sampling. So really, we were quite pleased about these results and saw a number of benefits across a variety of different things by incorporating this technique. So sort of in conclusion, we really need methods to figure out whether to trust machine learning models, and post hoc explanations can provide some intuition for us to help us figure this out. We sort of reviewed a number of shortcomings of post hoc explanations and looked at some promising approaches like modeling uncertainty to help overcome these challenges. So where are we heading next? So one thing we're really actively thinking about right now is how to make explanations a bit more interactive. So sort of what you guys saw is that with current techniques, explanations will just spit out a set of feature importances when you run them. But really, a lot of the time, like application users of these methods don't have the necessary context or expertise to decide which technique to run or how to interpret the results. And because we really want these to be valuable user-facing methods, we're thinking about techniques to make this happen. So we're thinking about like a natural language dialogue as one medium to facilitate more intuitive and useful like conversations with explanations. So this is one promising direction, at least, I think, for the future. So happy to open up to any questions now.
Okay, great. Thank you. Let's all give Dylan a virtual round of applause. And we have time for more questions. You can either unmute and ask, or also put your question in the chat if you'd like. So I'm curious in the sort of attacks you talked about in the start. I know you had these two classes, the counterfactual and the local explanation. But if you look at, like, let's say the kind of local explanation methods, I mean, how specialized is the attack to the method that is going to be used, right? If you built an attack, do you have to know whether they're going to use Lime or SHAP? Do you have to know what hyperparameters they're going to use, or is it more robust than that if you want to, hide your bad behavior?
Yeah, that's a really interesting question. Yeah, so far with that attack, we just considered you're going to know if you're going to use Lime or SHAP. Basically, all these methods have differing set of assumptions for how they go about sampling the perturbations. And most of the time, these are pretty heuristic choices. These are just choices that the designers of these systems have implemented for their particular package. So if you know like what those choices are and how they've biased the perturbation sampling, you can do this attack. Now, because there are similarities between the different packages, it could be possible that the attacks would generalize, and maybe by incorporating different types of sampling into the adversarial training procedure, you could attack multiple techniques. But one really interesting thing people have done since that work is develop maybe like a dozen or so like smarter sampling procedures that break these attacks effectively. So that's if you have a good way to sample from the data distribution to fit your perturbations, this attack will work. Right. So
okay.
There's a lot of work that's come since then that has addressed these issues as well.
I see. Make the perturbations more sophisticated, and yeah, that makes sense.
Yep.
There's a question in the chat. They ask for the charts with the plots on improving stability. I'm curious about what the metric you use to quantify stability is.
Yeah. So there's this. Basically, with this stability metric, the question is, if you perturb an instance slightly, how much does your explanation change? Right. So effectively, this is what this metric says. So if you just perturb an instance by a very slight amount, what is like the norm distance in your, like, I think it's like L2 norm or something like that, for how much the explanation changes. And then we took, for this particular graph, what we did is we like ran it for Lime, and then we ran it for our method, and then we just took the % increase or decrease in explanation stability, and then we plotted all that. So that's how you configure that. Yeah, Roy?
Hey, thanks for a great talk. I have a non-technical question. So in my mind, when you say explanations, definitely what you showed in the last slide, the interactive kind, is when there's someone listening to the explanation and then going, Okay, I understand. And so do you have any way of measuring that without user studies, or do you do user studies, or what?
Yeah, we try. So within the explainability literature, there's like basically a multitude of different techniques. People have tried to do these sorts of different things. Effectively, like one big thing people do is they have people, or they have like, for these works, we didn't run too many user studies, but like one big thing people do is they see within some locality in the model, if I give them a set of explanations, can people like simulate the model's behavior? And the idea is that if they see like 5 or 6 explanations and they understand them, they can say, okay, if I get this data input, this should be the model output. And if it matches up with what the model says, then these are good explanations. So that's one thing people do a lot to measure these sorts of things.
So just that, you're sort of working towards making the explanations more accurate. Mm-hmm. And that could actively make them less useful, right? And mm-hmm. You sort of need to balance that, right?
Yeah, definitely. Yeah, there's definitely a tensity between complexity and usability. So yeah, that is definitely something we're considering. Yeah.
Sounds good. Thanks for the explanation.
Yeah. Yeah.
Looks like Yaning Shin has a question.
Yes. Yeah. Thank you. Thank you for the great talk and the very nice work. And I was very interested in the analysis part. So, sure. I checked the paper also, and I see that the analysis gives very nice results on how many uncertainties you still need to sample given the S number of seed samples. So I was wondering, however, this sampling is done in sequential fashion. So, and it seems that you decide where to sample next based on previous observations. So does that mean that this analysis will be updated on the fly, meaning that when you sample an additional sample, you will have a different estimate on how many samples you still need to get? So not only limited from the initial seed samples.
Yeah, this is a good question. Kind of with the focus, so like with our estimate, it will say, effectively says if you randomly sample, this is an expectation how many perturbations you need. With the focus sampling procedure, you can get there a lot quicker. And because the focus sampling procedure is batched, basically what we do is if we reach the desired level of uncertainty, earlier on, we just stop the explanation.
I see. So does that mean that, so you mean that the focus sampling is done in a batch fashion, not in a online fashion?
Yeah, so we'll sample like 100 perturbations, sample a candidate set of like 10,000 more, only choose 100 of those, and so on and so forth.
So alternatively, you could also do like active sampling procedure, right? So based on the previous observation, you could update your posterior or distribution and decide how many samples you need to get next. Is that working?
Yeah, in some sense, maybe that's similar to what we're doing, because we do like hold on to the samples we've already gotten so far. But yeah, so for this work, we just basically just refit the explanation. But yeah, interesting idea.
Thank you very much.
Yeah.
Are there any other questions? Okay, well then let's all thank Dylan again for a very interesting talk.
Thanks.
And we'll be back next week, still virtual. We hope to hit some in-person events maybe later this spring, but we're sticking for at least the next couple of weeks with some more virtual talks. So I hope you'll be able to join us again.